Roots and radicals. Simplify. Sometimes you need to take a radical or a root of an expression that is not a perfect square or perfect cube, etc., right? Maybe the fourth root, you want it to be the perfect fourth power. To accomplish this task, you need to factor out perfect squares or perfect cubes or perfect fourth powers, if possible, depending on what the root is. It needs to match the root, all right? And so here with square roots of numbers, we only care about 1, 4, 9, 16, and 25. The reason is this is 2 squared, right? 1 is 1 squared. 3 squared is 9. 4 squared is 16. 5 squared. So what's the next perfect square after 25? 6 squared is 36. So look, we don't care if the number 3 goes into something because you cannot take the square root of it. The reason we care, we can take the square root of every one of those numbers. That's why we care. So let's remind ourselves of our perfect squares. And here's our list. Right? We can take the square root of anything that I circle here. Any of these numbers that get circled, I can actually take the square root of them. So if I can make this thing into 3 times 9, then I can take the square root of 9 and leave the 3 under the square root. Or if I get 2 times 144, I can take the square root of 144 and leave the 2 under the radical. All right? Same thing for cubes. With cube roots of numbers, we only care about 1, 8, 27. Why? Because 2 cubed is 8, right? That's 2 cubed. This is 3 cubed, 4 cubed. So the cube root of 64 is 4. The cube root of 27 is 3. I can take or apply the cube root to those numbers. What about 5? What is 5 cubed? That's right, 125. So 6 cubed, 216. We're supposed to be familiar with those things, but let's remind ourselves of them here. So again, I didn't go up and down here. I went side to side, but still I'm going to circle the numbers here. I'm going to circle the numbers that if I can make this thing 2 times 343, then I can take the cube root of 343 and get 7 and leave the 2 under the cube root. Or if I can get 3 times 8, right, then I can take the cube root of 8 and leave the 3 under the radical. So that's what we're going to end up doing with these perfect squares and cubes or perfect whatever power, if it's a higher power, higher order radical here. So when we take any root of a number, I will often say we applied the root. So when I factor it into 25 times 3, I'm going to apply the square root to 25 and get 5. Right? If I apply the root, that means I'm able to take the square root of it or take the cube root or whatever it happens to be. So I'm going to use the word applied sometimes. Okay, so when I say that, I just want you to know that's sort of a note here for you if I use that terminology. With exponents, all right, the exponents of variables, we divide the power by the root. So while we typically don't use mixed numbers in algebra, I find it actually beneficial here to consider mixed numbers in this scenario. So when you have a mixed number, for example, when you have 13 fourths, that's the same thing as 3 and 1/4, right? 13 or 4 goes into 13 3 times. That's 12 of them with 1 left over. That's my remainder, the 1, and we put the remainder over what we divided by, so that's where I get the 1/4. So this is the whole number part that I say goes into. So when I talk about the whole number of the mixed number is how many times the root goes into the power, how many times the root goes into. So how many times does 4 go into whatever that is? The power there, 13. How many times does 4 go into the power? Well, it goes into it 3 times. That's 12 of them. So that is what comes, that's what I'm talking about when I talk about that, and I'll talk about what happens to it in a minute. And then I'll refer to the numerator of the fraction as the leftover. So I have 1 leftover. My remainder, my leftover is 1. So I will talk about how many times something goes into it, and then the leftover. So again, just things that I might say as I go through this. All right, how many times the root goes into, okay, that part that I mentioned, that 3 on my mixed number up here. Remember we have 3 and 1/4? That 3 is going to be what comes out of the radical. So whatever my variable is, it's going to be that to the 3rd power, because 3 of those variables, that variable to the 3rd power was able to come out of my radical. Okay, I was able to apply the root to that part and get a 3rd power. And then the 1 left over, the leftover part stays under the radical. Okay, so whatever my variable is, it'll be that number to the 1st power, which I don't write the 1, will still be left over under my radical. All right. So here's my disclaimer, all right? And I'm going to have this disclaimer in most of my roots and radicals videos because every book I've ever taught out of, at every algebraic level does this, okay? At some point in the book. It doesn't do it for every section, but it does it at some point. So for here, when we simplify these, when we multiply, when we divide, when we add, subtract, I'm going to have this disclaimer, and then I have one more video that's down here at the bottom, roots and radicals, negative variables, okay? When you can have negative variables possible, then I will go over a few examples of that so you can see it just in case your book or the section you're in your book or your teacher says, hey, don't assume they're positive. How do we handle that? All right? So I want you to understand something. Even though I'm assuming that all the variables represent positive values in this video, that's not always the case. Sometimes your variables can be negative, and we know this. And I don't mean like negative x. I mean x could be negative 4. So I'm assuming x only is 4 here, or 7, or 13, or 1/2. I'm not assuming it's negative 4, or negative 1/2, or negative 17. Okay? So if your book or class does not restrict the variables, then you must remember this property right here. Square root of a squared equals the absolute value of a. See what I'm doing when I assume the positive values here? I'm eliminating the need to worry about the absolute value here. That's what I'm doing. That's why I do it. That's why the books do it. You don't have to worry about the absolute value here. So this is actually true for any even root resulting in an odd power. So what I mean is if I take the fourth root of something and I get a variable to the second power, that's okay. But if I get a variable to the third power, it's got to be an absolute value because it came from an even root. All right? So that's what I mean by any even root resulting in an odd power. All right. So again, for more on negative values, if negative values of variables are possible, then watch that video, Roots and Radicals, Negative Variables. All right. So what about the square root of 40? What about the square root of 40? Well, the square root of 40 is not a perfect square, right? My perfect squares, 1, 4, 9, 16, 25, 36, 49. And look, I just rattle them off. I'm not looking at them. You need to get to the point where you can say them like that. All right, so it's in between 36 and 49, so it's not one of those. It's 6 point something, but I don't know what it is. So we're not worried about decimals. We're going to say, okay, well, how can I get an exact value for this? Well, as I go through my list, 1, 4, 9, 16, 25, 36, and when I get to 49, I'm too big, right? So then I don't need to go past 49. There's no way it can go in there. So is there any one of these numbers here that goes into 40? And actually, there may be more than one. You want the largest one always. You want to get the largest one if you can. So here, 4 does, right? 4 goes into 40. Does anything else go into 40? 9, nope. 16, nope. 25, nope. In fact, when you get more than halfway through this number, you can be done, okay? So here, 4 goes into 40. So how do I do that? Well, it's going to be the square root of 4 times 10. I like to write my perfect square first. There's nothing wrong or right about that. It's not one way or the other. This is what I like to do. And the other thing that I like to do is underline the thing that I'm going to apply the square root to. Now I said that word apply. I'm going to apply the square root to 4 because I know the square root of 4 is what? 2. So then I'm going to take this. What technically happens here is I'm taking the square root of 4 times the square root of 10, and the square root of 4 becomes 2. Okay? So that's what is really going on there. So this is going to be 2 and then square roots of 10. Not 2 on it. I know people say on it. I don't know where I need to look the history of that up. I don't know where it came from, but it's not on it. This would be 2 on the square root of 10, and that's not really anything. Okay? So it's 2 times the square root of 10 or 2 square roots of 10. If your teacher says on it, that's fine. Let them say on it and just know what they mean. All right? I just don't think it's on it, and I don't understand that terminology. All right, so 2 square roots of 10 here. And the way I know I'm done, do any of my perfect squares, 1, 4, 9, 16, 25, go into 10? And by go into, I mean divide into it. And the answer is no. So 2 square roots of 10 is my final most simplified answer there for the square root of 40. All right, so what about the square root of 28? Well, again, what goes into 28? Well, 1, we don't need to check 1. 1 goes into every number, and that doesn't help us. So does 4, 9, 16, 25, then it gets too big. So 4, and sometimes I won't even write it out. I'll just mark through this and put 4 times 7 and underline my 4. So the 4 comes out as a what? 2. When I apply the square root of 4 is 2, but I cannot apply the square root to 7 because it's not a perfect square. I can with the calculator and get a decimal, but it's not a perfect square, so then square root of 7. So this is 2 square roots of 7, and again, nothing will divide out of this. In fact, there's no factors of it that is a perfect square. So what am I looking for? Am I still looking for 1, 4, 9, 16, 25 on this one right here? Nope. Why not? Because we're talking about cube root, which means we want perfect cubes, right? And that list was what? 1, 8, 27, 64, 125, and then it got big fast, right? And I told you to know these two, 216 and 343 for 6 and 7. But they get real big real fast. So if you just get down to 125, that's probably good enough, but just know that especially on your software packages, it could get bigger, a lot bigger. So does 8 go into 250? No. What about 27? Nope. 64? Nope. 125? Wait a minute. This is going to be the cube root of 125 times how many? 2. So this is going to be the cube root of 125, and I'm going to show it again here, times the cube root of 2. This becomes just good old 5. Cube root of 125 is 5 times the cube root of 2. And like I mentioned in an earlier video of roots and radicals, I wrote my 3 first and built my radical around it. So therefore there was no doubt here. Like if I put the 3 in front of the radical and then wrote the 5 here, am I writing 5 cubed or 5 times the cube root of something? Right? So that's where it's important to be careful about what you write, that pay attention to detail piece. Okay? Because I'll say it again, the thing that I think most of my students need to get from my class, because many of them are checking college algebra off a box, and if they can check that off, they're doing a backflip, cartwheel, somersault with a twist and a tuck and a half pike and whatever, and they're just going to have a pizza party if they pass. And so for that student, the next time they solve a quadratic equation is going to be when their kid's in 10th grade in algebra or 9th grade in algebra, and they're like, "Can you help me, Mom or Dad?" Okay? So what they need to be able to do to help them that they get from math is solve problems. Don't be a problem creator, be a problem solver. Be efficient, okay, and pay attention to detail. If you can do those 3 things, you'll not only get better at math automatically, you'll get better at everything in life you do. I don't care what you do in life, you'll get better at it, okay? You'll even get better at video games. Oh, I just caught some of y'all. Y'all like, I'm in. I'm all in. All right? So then, better at sports, better at managing Walmart, better at whatever you do, running a Fortune 500 company. So then here, cube root of 32. So 1, 8, 27. Well, I noticed that 8 goes into 32 with odd roots of negatives. Remember, an odd root of a negative is negative. So then you include the negative with the perfect cube here. So what I'm going to do is I'm going to say this is the cube root of negative 8 times 4. And then negative 8, I'm going to underline. The cube root of negative 8 comes out as what? Negative 2, and then what stays under the cube root? The 4. It can't come out because you cannot apply the cube root to 4. All right? So negative 2 cube roots of 4, or negative 2 times the cube root of 4 is the cube root of negative 32. All right? So let's keep working on these, keep trying to figure out how we're going to break these up and divide them up and separate them and that kind of business. So the square root of 27x. So far, we've only seen numbers where we've had to break them up. Now we're introducing some variables. Here we have x. The next one we have y squared. All right, so let's do the numbers like we've been doing them. Is 27 a perfect square? And be careful, that's a perfect cube, but we're not talking about cube roots. We're talking about square roots. Remember, there's an understood 2 there. It's understood most everywhere else in math, it's 1, but here it's 2. All right, and then when you get to some other things in math, you may have a couple of other understoods, but here we have an understood 2. So then the square root, perfect squares, 4 doesn't go into 27. What about 9? Yep, 9 times what? 9 times 3. So I'm going to underline my 9 because the square root of 9 is what? 3, right? The reason I can do that, the square root of 9 equals 3. That's why I have this arrow right here, because this is under a radical. All right? So what's left over under my radical? This 3 stays under here. Look at this x. Here's how you know if you can bring a variable out. It's that whole goes into part, right? How many times does 2 go into 1? Well, it doesn't, right? If it doesn't go into it, in fact, if this power is less than this, then it cannot go into it, right? Never. You're not going to bring anything out that's less than that. The other piece of that is when you finish simplifying these, when you finish breaking them down, however you want to say it, then you will always have powers in here that must be strictly less than the index. You cannot have an x squared left over in a square root. That means you didn't finish it. It's not done. You got more to do. All right. So here, the x will not come out. None go in there, and there's 1 left over, so it stays under the radical. Now, this has got a lot of space in it. So aesthetically, let's take this and say 3 times the square root of 3x and kind of put it nice and neat together. That's the same thing. I just don't have all this empty space here that makes it look like something belongs there. I left that space because I wasn't sure, was I going to have to bring x's out here or not. I didn't have to in this one. So I left that space for that purpose, but then it didn't. Nothing came out. So here, let's look at this one. The cube root of 54. Now, 64 is a perfect cube, but is 54 a perfect cube? No. Does 8 go into 54? And you're tempted to say yes, but 8 times 7 is 56. So 8 does not go into 54. What about 27? Yes, 27 times what? 2, right, is 54. What is the cube root of 27? It's 3, right? This comes out as a 3. And then under my cube root, I'm left with the 2. Can I bring any y's out? Okay, if you said no, why? Because how many times does 3 go into 2? Well, it doesn't, right? If 2 is less than 3, nothing comes out. We already said that. So then this y squared stays here. Again, I left space for any y's that came out, but they didn't. So then I'm going to just close the gap there. 3 times the cube root of 2y squared. If you'll notice, every time I write a root bigger than square root with an index here that you see, I'm always going to write, 5th root, cube root, 4th root, 16th root. We don't do any with 16th roots, but I'm going to write the root first and then build the radical around it. So again, just a habit I want you to get into, but that's attention to detail. All right? Pay attention to that detail. So 3 times the cube root of 2y squared here. All right? So let's work some more of these. The square root of x to the 7th power. Okay? X to the 7th power. The square root of x to the 7th power. So then I say, how many times does 2 go into 7? 7 is bigger than 2, so we know we're going to bring some out. So if I think about that as a mixed number, right? 7 over 2. How many times does 2 go into 7? 3 with how many left over? 1. So that's 3.5. So then what we have here, x to the 3rd power. That's the 3 here. And then under the radical, x to the 1st power. That's this one here. Do I write that 1? No. I just wrote it there for emphasis sake right now. I don't really write that 1. I don't really write that 1. So that's just, this 1 goes here, and we're left with x cubed times the square root of x. I'm just going to rewrite it because of all those arrows I have up there that look awful. Okay? X cubed times the square root of x is the square root of x to the 7th power. So I'm going to do the same thing on the next one, is just have x's and y's in the same problem. But the key is here, this is all one term. If there was a plus or minus right here, you couldn't do what we're about to do. You can only do that when it is one term. Yes, it's 2 factors. The x's are a factor and the y's are a factor. Okay, but each factor multiplied together gives you one term because everything's multiplied. All right, that's why factoring is so important, because you keep it into one term. So here, this is one term. So since it's one term, then I can say this is going to be x, and then if I say, how many times does 2 go into 8? Well, that's 4 times, right? With how many left over? Well, 2 goes into 8 exactly 4 times. There's none left over. So how many x's do I have under my radical out here? I brought 4 out, and I don't have any x's over here, right? For x, I don't have any, none. Because again, if I say 8 divided by 2, or 2 goes into 8 4 times with none left over, okay? Not a single one left over. So then I look at my y's. I say, how many times does 2 go into 5? Or what is 5 divided by 2? It's 2 and 1/2, right? So here's the y's, the 2 that come out, and then the 1 y left over. The 1 y left over under the radical. And since I only have the one thing left over, I'm going to shorten that up a little bit so it looks a little neater. So x to the 4th, y squared, and then times the square root of y. The square root of 48x to the 3rd, the square root of 48x to the 3rd power. Now we're mixing numbers with variables. How many terms do I have in here? 1 term. Very good. It's 1 term because there's no plus or minus separating terms. Now I have 2 factors. 48's a factor, and then x to the 3rd's a factor, right? So then I guess you could say x is a factor raised to the third power, but still, I have two factors in here. So since it's one term, I can try to break 48 up, and then I can do my power thing with the x's. So 48 works just like the numbers did. Does 4 go into 48? Yes, 4 times 12. But is there a bigger perfect square than 4? What about 9? 9 does not go into 48. What's next? 16. 16 times 2 is 32. 16 times 3 is 48. Look at that. So 16 works. Anything bigger than 16, 25, and then 36 and 49 is too big. So the biggest one is 16. So I'm going to say this is 16 times 3. The square root of 16 comes out as a 4. And what's left over under the radical? The 3. Okay? And then since 3 is bigger than 2, that means I'm going to have some x's out here and possibly some in here. Okay? If there's any left over. So what do? I say 2 goes into 3. How many times? 2 goes into 3 one time. That's 2 of them with 1 left over, right? 2 goes into 3. Mixed number 1 and 1/2. This one is this one. This 1/2. The 1 makes that 1, right? The numerator there tells me. So 4x, and again, I have a lot of extra space here, so if you want it to look a little better, you can just write it all together here. 4x square root of 3x, but that's, I would accept that. That's close enough, okay? Of course, if you've ever had my class, you know I have answer boxes. That's where I want your answers. All right? So let's keep looking at some of these. Let's keep simplifying these and breaking these up and seeing what's going on here. All right? So the cube root of x to the 11th power. The cube root of x to the 11th power. All right? So how many times will 3 go into 11? So if I think about 11 thirds, right, what is that mixed number? 3 and 2/3. So it goes into it 3 times, right? That's the goes into part. And then the numerator is 2. So that means I have x to the third power. That's this right here. Comes out front, right? Outside the radical. X to the third power. And then under the cube root, the radical, I have what? X to this power, which is 2. So x cubed times the cube root of x squared. For this one. And then the next one, my tribute to PVC pipe, right? So the cube root of p cubed v to the 17th c squared. How many terms is it? It's one term, right? There's no pluses or minuses. How many factors? There's 3 factors, the p's, the v's, and the c's, right? But it's still one term. So I'm trying to, each time I talk about this, I'm trying to help you get your terminology down pat, all right? So just to remind you, I've said it before, we do a really good job in math, and I say we, I'm talking about math teachers. We do a good job of teaching you steps. You can learn some steps, you will memorize some steps. The problem is you'll just memorize what to do for that problem. We don't do a real good job of teaching you to recognize what to do. Okay? So I'm trying to teach you recognition here. This is recognizing this is one term with 3 factors, okay? And that terminology will help you with that, okay? That's another thing we're not real good at making you, because we're numbers people. We're not word people. We usually are pretty good at details, but we're still, the words that you say sometimes, we just like, if you can just get this right, we don't care what word you use. And we shouldn't be that way. We should force ourselves and you to use the correct terminology, because then math would be so much nicer and cleaner. All right? So here, this is going to be what? Well, one term, I can take each one. So how many times does 3 go into 3? It goes into it one time, right? 3 over 3 is 1. That mixed number is 1. There's no fraction left. So then when I bring it out, I have a p. And under my cube root, guess what? I don't have any p's. There's not any p's. So don't put any in there, right? 3 goes into 3 exactly once. Bring that 1 out front, that 1 p out front, and then there's no more p's. What about v? How many times will 3 go into 17? Well, if we talk about 17 over 3, that's going to be 5 and 2/3, right? Because 5 times 3 is 15, and 17 minus 15 is 2. That's where those numbers come from, right? So then we have a v to the 5th power, and in here, v to the what? The 2nd power. The 2nd power is here. The 5th power is out here, right? And then what about c squared? Is this number bigger than my index 3? No. So can any c's come out? No. 3 doesn't go into 2, so you just leave your 2 c's in there. So your c squared. So p v to the 5th times the cube root of v squared c squared. Is there any doubt on what I wrote up here, what my root is? My index? No. 3. If you wrote it this way, if you wrote this, p v to the 5th times the cube root of, Oops, I just did it because I can't help it. All right. V squared, C squared. So I did a couple things wrong here. One is, what does this look like? This looks like V to the 53rd power. That's no good, okay? And then over here, notice this thing stops about halfway over the C squared. So is my C squared part of my radical or not? So make sure that extends out fully, and instead of this 3 being here, put that 3 down here, and now there's no doubt that's V to the 5th power, and that's cube root, okay? So again, that's just some detail to pay attention to, and things that sometimes we math teachers even get a little crazy and not show that much detail when we write it. But we should always write it correctly, and then we should expect the same excellence out of you, okay? You, the student. The cube root of 24, x to the 13th, y to the 8th. So again, how many terms is this? This is one term. One term. So then, is 24 a perfect cube? No, but it is what? Is it 8 times 3 maybe? So then if that's the case, we'll come down here. This 8 comes out as a 2, and then under my cube root, the 3 stays under there, right? The 3 stays under there. Cannot apply the cube root to 3. You have to leave it under the cube root. Doesn't get applied. This 8 had the cube root applied to it, and it became a 2 when you took the cube root or applied it. So then here, x to the 13th. How many times does 3 go into 13? Well, 3 goes into 13. Let's see. 13 over 3 is 4 1/3, right? 4 times 3 is 12 with 1 left over. So guess what the 4 is? The 4 is the power out here, x to the 4th. That's this 4, okay? And then how many x's are left in here? 1, because this 1 says there's 1 here. So 4, x to the 4th out front, and then x under the radical. And then y to the 8th. How many times will 3 go into 8? Well, if we think about 8/3, then we get what? 2 2/3. So this 2 is this one, right? It's going to be y squared. And then this 2 is this one. That's also going to be y squared, but that y squared is under the radical. It's still inside the radical there. So 2x to the 4th, y squared times the cube root of 3xy squared. So that's a perfectly legitimate answer there, right? And it's not too much space in there. There's a little bit of space, but there's not too much for me to confuse myself too much, I hope. So I hope this helps with simplifying radicals, right, and roots.